Okay, welcome everybody to another edition of the Virtual Time Series seminar. It's my great pleasure today to introduce Anders Kock from Oxford, who will be talking to us about high-dimensional Gaussian and bootstrap approximations for robust means. And he's joined by Jesper Riis-Vestergaard as the guest panelist. So thank you very much to both of you. And Anders, the floor is yours.
Okay, thanks for having me. So I'll talk about joint work with David Breinerstorfer, who is in Vienna now. And we've been interested in the asymptotic properties of Winsorized means with a view towards using them for hypothesis testing for a while. So let me introduce you the background for this problem here. Oh, and now I have to switch slides. So consider a setting where you observe n random vectors taking values in Rd. They're IID, and they have a mean of mu. By the way, when I highlight, you can see it. Yeah, okay. Then you may form the centered and properly normalized sums in a setting where D, the dimension of the space within which the vectors take their value, is fixed, but you let the sample size n tend to infinity. It's well known by central limit theorem that Sn converges in distribution to a normal with a mean of 0 and a variance-covariance matrix being that of x1. Recall, we're here in an IID setting. Now, such Gaussian approximations have played a huge role in classical statistics because they underlie asymptotic coverage probabilities of confidence intervals or asymptotic size control of many typically used tests. But now, in recent years, it is more and more common that one observes many characteristics on each individual object, which is typically modeled as D, the dimension being large compared to the sample size n. So for that reason, there's been a great interest in Gaussian approximations to the distribution of Sn when D, the dimension of the data, is large relative to the sample size n. In particular, increasingly refined upper bounds have been established on the Gaussian approximation error over various classes of sets. So you consider the probability of Sn, your properly scaled and centered sum, falling within a certain set, and compare that to the probability of a normal distribution with a mean of 0 and the same covariance matrix as x1 falling within that set. You take a supremum over your favorite class, calligraphic A. Now the size of rho n, this Gaussian approximation error, depends obviously on the complexity of the class A. It depends on how large D is relative to n, and it may also depend on which further assumptions one is willing to impose on the x's. In particular, I focus on the number of moments that the entries of the x's possess shortly. Now, one thing I said that this Gaussian approximation depends on is the class of sets A. A particular class of sets that has received lots of attention is the class of hyperrectangles, which I denote here by calligraphic H, which is simply default products of intervals in R. So for each coordinate j, it lies in the interval from aj up to bj. Other sets of interest may be convex sets, which of course a superset, whoopsie, wow, I went all the way to the back, fantastic work. Apparently it's a great idea to build hyperlinks into your presentation. So other classes of sets of interest are convex sets, which are supersets, of course, of these hyperrectangles, and there's also been some attention given to Euclidean balls. In this talk, I'll focus on hyperrectangles. Well, why have hyperrectangles received particular attention? Well, because it's possible to prove that this Gaussian approximation error over hyperrectangles can tend to 0, even when the dimension D increases exponentially in n as n tends to infinity. And another reason is abstracting from sigma, the covariance matrix of the data being unknown in practice. Such Gaussian approximation justify the use of Gaussian critical values, call them CD alpha, for testing hypotheses based on max type statistics here. Because if you have a sequence CD alpha satisfying under normality here, that the probability of the maximum of a normal vector with a mean of 0 on variance-covariance matrix sigma falls above CD alpha, if that probability tends to alpha, then if furthermore this approximation error here tends to alpha, tends to 0, well then of course also the probability of my statistic falling above CD alpha tends to alpha. That is, I can construct test with the desired asymptotic size if I can establish such Gaussian approximations over hyperrectangles. However, it turns out that such high-dimensional Gaussian approximations for max-type statistics are, in a sense, a light-tailed phenomenon. By this, I mean the following. Because for any number of moments m, strictly greater than 2, but strictly less than infinity, that the entries of your data vectors x may possess, and for any alpha, which strictly between 0 and 1, for any sequence CD alpha satisfying 1, that is, under normality, here it holds that the maximum of this Gaussian vector falling above CD alpha tends to alpha. The following is the case. There exist ID random vectors x1 up to xn in Rd such that all entries have a distribution Pm that depends neither on n nor d. This distribution Pm has a mean of 0, a variance of 1, and finite mth absolute moments. And furthermore, it is the case that if the dimension d grows a little bit faster than n to the power m half minus 1, where m, recall, is the number of moments that the entries of my vectors x possess, well then, if the dimension grows faster than this threshold, it is the case that the probability of my statistic falling above this candidate critical value CD alpha minus the probability of the Gaussian falling above CD alpha, the limit superior of this sequence is 1 minus alpha. Now, we know by construction that this probability here tends to alpha, because this is by construction, CD alpha by construction is a sequence of asymptotic size alpha critical values for this test statistic here. That is simply following from here, equation 1. So what this here says is that if I use critical values from an asymptotic Gaussian approximation, then if dimension grows faster than m half minus 1, well then actually it's the case that the asymptotic rejection frequency, that is the probability of a max-type statistic falling above the sequence of critical values, is not alpha, but it tends to 1 actually. This is of course alarming, because I think my test has asymptotic size alpha based on this Gaussian approximation, but in fact it tends to 1. So that is to say, when dimension increases faster than this threshold here, the Gaussian approximation breaks down completely. Now let me try to illustrate this. So here I let all xij's be iid across not only I, but also for each fixed vector, each entry is independent, and they all have a distribution that is the same distribution, that is a t-distribution with 3 degrees of freedom. So below I provide some pp plots. First here for sample size being 100 and for dimension being 100. On the x-axis, I plot the CDF of this statistic here, the maximum of Gaussians here. The black line is simply the 45-degree line. So that is corresponding to also the CDF of this max statistic on the y-axis. But more interestingly, I plot also the CDF on the y-axis of my actual statistic of interest. That is the blue line here. What we see is the blue line lies below the black line. That is to say that my statistic has heavier tails than a Gaussian here. In particular, at this point down here, where one would pick out the 5% critical values in the Gaussian, well, then actually my max statistic has a probability of, say, 15% of falling above that critical value. And things get much worse if I hold dimension n fixed at 100 still, but increase dimension to 1000. Then out here in the tails, we see that whenever I have my 5% Gaussian critical value, Sn actually has a probability of whatever 50% of falling above that. And we know from the theoretical result on the previous slide, if I were to increase dimension even more, well then this probability here would actually tend to 1. On the other hand, whoa, what was that? On the other hand, it is also the case that whenever the dimension grows a little bit slower than n to the power m half minus 1, where then this Gaussian approximation error over hyperrectangles tends to 0. So even if I take the supremum over all hyperrectangles, then the Gaussian approximation error tends to 0. That is to say, if there's a critical phase transition occurring at d equal to n to the power m half minus 1. If d grows a little bit faster than that, we know from this result here that the approximation error, the approximation breaks down completely. If it grows a little bit slower than that, we know from this result here that the approximation error tends to 0. So this is there's a moment-dependent phase transition in the sense that the location of the phase transition depends on m. So consider the case of m equal to 3. I mean, since it's a time series seminar, often for time series data, in particular financial data, one may think, well, heavy tails omnipresent, so maybe I'm not willing to impose that the entries of my data have more than 3 moments. Well, then that is to say, then this implies that the phase transition occurs already at n to the power 3 half minus 1. That is at d equal to n to the power 1 half. So the Gaussian approximation over hyperrectangles breaks down already when the dimension grows faster than square root of the sample size. A far cry from dimension growing at an exponential rate. Okay, so this was sort of the negative result. That is, Gaussian approximations for plane sums can break down at this critical threshold here if one only imposes the entries of the xi to have m moments. I'll talk more about consequence for testing later on. Now, motivated by this phase transition, there's a recent paper from last year by Lucas Resende who replaced the sums Sn by suitably trimmed means. Then, for such trimmed means, he obtained Gaussian approximation for the distribution of maxima of trimmed means, even when the xi only possess m strict greater than 2 moments and d grows at an exponential rate in n. Therefore, this polynomial growth barrier that I just showed you can be broken by considering trimmed means instead of plain sums. Furthermore, as an added benefit, this trimming implies that the approximations, the Gaussian approximation, remain valid even if some of the xi's have been adversarially contaminated, that is, in the presence of some outliers. We know, of course, that sums that have a breakdown point of 1 over n. I can change the value of my sum Sn to any desired value by changing only one of the summands, so they're extremely fragile in that sense. Now, despite the progress in Resende, there are some limitations. One limitation being that the amount of trimming depends on m, the number of moments that the x's possess. M is typically unknown in practice, I would dare to say. Furthermore, the exponential growth rates of dimension have a suboptimal dependence on m, and Resende focuses solely on the distribution of maxima of trimmed means. Now, to use these Gaussian approximations to derive power properties of ensuing tests, one needs Gaussian approximations over the full family of hyperrectangles and not only for the maxima themselves. So to address these 3 shortcomings, we study here Gaussian approximations to Winsorized and trimmed means in this paper, for which 1, the amount of Winsorization or trimming does not depend on m, instead it adapts to it in a data-driven manner, so that is addressing this first shortcoming up here. 2, we allow the dimension to increase at an exponential rate in n, even when one only possesses m strictly greater than 2 moments. Of course, you can see here if m is close to 2, well then the exponent is not very large, so the growth rate does still depend on m. And thirdly, to address this point here, we provide approximations to the distribution of Winsorized means in Rd over the full family of hyperrectangles. Okay, so I mentioned 2 minutes ago adversarial contamination because the trimmed and winterized means are robust to this. What do I understand by an adversarial contamination? Well, by this I mean the following. So before getting access to my data, x1 up to xn, an adversary is allowed to contaminate it. In particular, an adversary can inspect the sample and return a corrupted sample, which I denote by x1 tilde up to xn tilde. However, the corrupted sample must satisfy that only a fraction of at most eta bar of the observations have been changed. So only a fraction of eta bar n of the xi tildes can be different from the xi's. Which observations my adversary changes can depend on the data, and to what value he changes it can also depend on the original data. Okay, now, in case you're not so interested in robustness, for the remainder of the talk, just think of the x tilde, the data that I actually observe, as being equal to the xi's. That amounts to, of course, no contamination, eta being equal to 0, okay? Yeah, here I'm just saying that adversarial contamination is not invented by us. In fact, in recent years, it's been a popular test bed in robust statistics, and here's a bucket of references. Okay, throughout the talk, we impose the following assumptions. So, as I already alluded to, we consider the case where the raw, uncontaminated data, x1 up to xn, is IID and takes values in RD. The entries of my data have mth moments for some m strictly greater than 2. Furthermore, we'll assume that the variances of the entries of x are bounded away from 0 or bounded from below by some b1 to the power 2. Also, the m-centered moments are bounded from above by some b2. And finally, the actually observed contaminate random variables are denoted by x1 tilde and satisfy 2, that is to say, they satisfy that at most a fraction of eta and bar of the observations have been changed by the adversary. Okay? Good. So in a nutshell, what we're saying is IID data, variance is bounded from below, centered mth moment bounded from above, and only a fraction of at most eta of the observations have been contaminated. Okay, so I said we're interested in Windsorized means in the course of this talk. So what do I understand by Windsorized means? Well, for any real numbers, x1 up to xn, we denote by x1 star up to xn star the non-decreasing rearrangement. And I then define for fixed alpha and beta, alpha less than beta, my Windsorization function. The Windsorization function simply leaves x unaltered if x is between alpha and beta. If x falls below alpha, the Windsorization function returns alpha. If x falls below beta, it returns beta. So it looks like, you know, okay. Good. Now we establish first Gaussian and bootstrap approximations to the distribution of centered and Windsorized means. So I denote these by SNW, where the jth coordinate of SNW is simply given by now my contaminated data, xij tilde, evaluated here in the Windsorization functions, where the Windsorization points are alpha j hat and beta j hat, where alpha j hat is the lower epsilon order statistic of my contaminated data. Beta j hat is the upper epsilon order statistic of the contaminated data. So you can see all that has changed compared to the plain sums is that now we Windsorize the data instead of plugging in the raw data itself. And potentially there's contamination because the data X could be contaminated. That's why there's a tilde now instead of the raw data X. Okay. Notice that alpha j hat and beta j hat do not depend on M. That is the difference to the trimmed means studied in the end. There, the location of trimming in his paper depend on m, which is typically unknown. However, we must apply an epsilon n here. So what do I have to say about the choice of epsilon n? Well, we study epsilon n of the following form. So we suppose that we know an upper bound on the fraction of contamination. Yeah. Then epsilon n is of this form here. Sum lambda 1 times eta n, where lambda 1 must be strictly greater than 1. It is clear that if, say, 10% of the observations can be contaminated, or amounting to eta being 0.1, well then I must also Windsorrize at least 10% of the observations, because otherwise the adversary can still manipulate the statistic to its heart's desire. He can give it any value. That is why lambda 1 must be greater than 1. And then I add lambda 2 times some sequence here that tends to 0 under the assumptions that we shall make. In particular, in the canonical case of eta being 0, so no contamination, which is a case one always studies when looking at Gaussian approximations for plane sums, well then one can choose lambda 2 equal to 6, say. So then we would choose eta equal to 6 times this sequence here, and the theoretical results that are shown in the sequel are valid for that choice of eta here. So you would choose the lower epsilon order statistic, with epsilon being 6 times log dn over n, and beta being 1 minus epsilon times n here. So that upper epsilon order statistic here. So there are no unknown quantities, so it's fully feasible, this implementation here. Okay, well, I now define the following Gaussian approximation error here. Take a look at the probability of my Windsorrized mean vector falling within a given hyperrectangle, and I compare that to a normal distribution with a mean of 0 and a variance covariance matrix being that of my uncontaminated data, x1, and take supreme over all hyperrectangles. Now the goal is to show that this here either provide an upper bound on this for any fixed n, so a finite sample upper bound, or alternatively that it tends to 0 asymptotically. So in the talk, I'll only present sufficient conditions for this to converge to 0. However, this convergence follows from more involved finite sample upper bounds on rho nw here in the paper. In particular, these finite sample upper bounds in the paper also reveal over which classes of distribution one can expect uniformity in this convergence to 0. I mean, the answer is sort of obvious. Uniformity can be achieved over such distributions for which variances are bound away from 0 and centered mth moments are bounded from above. But I'll not talk more about this in the course of this talk. That is what I want to say. Yeah. So under this assumption 1, IID sampling, variances bounded from below, centered mth moments bounded from above, and at most a fraction eta of the observations being contaminated, one has the following. If the amount of contamination satisfies this here, so there's sufficiently little contamination, and dimension grows sufficiently slowly, well then, if we choose epsilon in the way that I described loosely a slide ago, but made precise in the paper, one has that the Gaussian approximation error over hyperrectangles for Windsorrized means tends to 0. So this holds for any m strictly greater than 2. So consider the case where there's no contamination, for example. Then this condition is trivially satisfied if eta is equal to 0. But then all we have to see here is that the dimension can grow at an exponential rate in n, even if I only have a little bit more than 2 moments. So this is in stark contrast to Gaussian approximations for sums, which in the beginning of the talk I showed you break down whenever the dimension grows faster than a polynomial rate here. So for any m, the Gaussian approximations for plane sums break down when dimension grows faster than n to the power m half minus 1. So they cannot generally grow at an exponential rate. This is in stark contrast to Windsorrized means here, where I can get an exponential growth rate of dimension in the sample size n, even when I only have fixed number of moments m. Okay, that is what I want to say about this slide here. Now, what is the proof strategy here? So, how do we go about showing this Gaussian approximation? Well, the first thing we do is to show that these order statistics here, that was the lower epsilon order statistic of the contaminated data and the upper epsilon order statistic of the contaminated data, are close to the population epsilon quantile of the uncontaminated data and the population upper epsilon quantile of the uncontaminated data with high probability. This allows us to replace my, so to speak, random winsorization functions, but this means these random winsorization locations by these population quantiles instead. That is to say, I keep changing slides inadvertently. My winsorized means here, which of course defined here at the random winsorization locations, the lower and upper epsilon order statistic respectively, I replace this by phi n being this function where I now windorize at fixed deterministic population quantiles. So that's why I have this squiggly equality here. It's an approximation. Once I have this, what I do is to subtract phi n evaluated at the uncontaminated data. That here I add it back in. I subtract the mean of phi n evaluated at the uncontaminated data, and I add it back in here. So now I have three terms. The first term I n j1 here for the jth coordinate. This gives me the effect of contamination. If there's no contamination, then of course the x tildes are just equal to x, and clearly this term here is 0 then. However, even if there's some contamination, by virtue of these phi n's being bounded functions, now I can limit the effect that an evil adversary can, screw up my statistics by. Furthermore, recall, we also only allow a fraction of at most eta bar of the data to be contaminated. That is, at most, eta n times n of these summons differ from 0. So it's conceivable that I can show, under the assumptions I've given you in the previous slide, that this term here is sufficiently small. The third term here somehow gives me the effect of quote-unquote wrong centering. So here I have subtracted not the mean of these guys here, but the mean of the uncontaminated data itself, the mu's. But it's also conceivable here that since epsilon here tends to 0, these quantiles, the lower quantile tends to the lower bound of the support of the axis, while the upper quantile here, if epsilon tends to 0, tends to the upper bound on the support of the axis. So one can show that also this difference here tends to 0 sufficiently fast. Now, this term here is a sum of IID random variables with a mean of 0, obviously, because I've centered them. Also, these are bounded functions, meaning they possess all moments. So I can now apply existing high-dimensional central limit theorems from the literature that typically impose sub-exponential tails. This is now trivially satisfied for these guys here. To show a Gaussian approximation for these terms here that allow for dimension to grow at an exponential rate in n. And this are then combined with showing that these two guys tend to 0 sufficiently fast. There's one more small twist, namely that the variance-covariance matrix of this vector here is not sigma itself, but it's the variance-covariance matrix of the winsorized data here. But by the logic I gave you up here, since the winsorization location tends to the lower bound and upper bound of support of the axes themselves, one can show that the variance-covariance matrix of these guys here converge sufficiently fast to the variance-covariance matrix sigma of the raw uncontaminated data. Yeah? This is the idea in the proof. And since this is a time series seminar, one way of extending these results to time series would of course be to look into which high-dimensional Gaussian approximations exist for time series data. Now this here, to show this is small, doesn't really depend on things being independent, and neither does it here because it's just measuring the effect of contamination. So there's great hope. In fact, I'm rather sure it's possible to extend these results to time series data. The point where dependence, again, sorry about the point where dependence really enters is when one wants to apply high-dimensional central limit theorems to these terms I2 here, but such results also exist for time series as paper by Zhang and Wu, for example. Okay. Now, sigma in practice is unknown.
Hans,
Yeah.
can I cut in? So can you go back one slide to the decomposition there? So at what point does the geometry of the sets play any role here? Does the hyperrectangles play any role at this
Yeah,
stage?
here it plays a role in the sense that I said these here have to be sufficiently small, and at some point you use to what does sufficiently small mean? Well, it means you now get a normal distribution plus a little bit extra here, so you use some Gaussian anti-concentration inequalities over hyperrectangles here. Yeah? And particularly, you can also show that the maxima of these guys is small. Had you looked at other types of sets, it may be the case that you have to show these guys are small in other norms than the supremum norm. Does that make sense?
Yes.
Yeah. Okay. So we've shown this Gaussian approximation here, that namely that the probability of my feasible statistic falling within a hyperrectangle is close to that of a normal distribution with a variance of 0 and a variance covariance matrix of sigma. Of course, in practice, I don't know sigma, right? So the next thing I would do is to address that sigma is unknown. And this we do by quote-unquote classic techniques. It's not really us who invented this. We do the following. So sigma is unknown. So the theorem 2, trust me, it's a theorem I just showed you, and the Gaussian approximation cannot be directly used for statistical inference. So, as is the case for bootstrap approximations to the distribution of plane sums Sn, one can make use of Gaussian to Gaussian comparison inequalities to solve this issue. Because if you have two normal distributions, both with a mean of 0 but different covariance matrices, well, then you can upper bound the probability uniformly over hyperrectangles here. The difference between those probabilities with the different covariance matrices in terms of the maximum entry-wise distance of the covariance matrices. So this opens the door to me using an estimator of this variance covariance matrix sigma here, if this estimation error of my estimator is so small such that this right-hand side here vanishes. Yeah? That is to say, I try to make that more precise on the next slide. So we can exhibit an estimator, sigma n tilde, say, of sigma n, satisfying that the error in the maximum entry-wise distance multiplied by log d to the power 2, well, why log d to the power 2? Because it enters here. If this tends to 0, well, then I can instead of sampling from this infeasible normal distribution with a mean of 0 and an unknown covariance matrix, I can condition on the data and sample from a normal distribution with a mean of 0 and this variance covariance matrix here. So how do I get such an estimator? Sigma n tilde is of course the next question when I have adversarial contamination of the data and I'm only willing to impose a little bit more than 2 moments to exist. Well, one guess is, of course, the sample covariance matrix. And this can indeed be used for d growing at an exponential rate in n if there's no contamination and the xi's have sub-exponential entries. Okay? Then one can show that the sample covariance matrix is precise in this maximum entry-wise metric here. Not in other metrics such as the spectral norm, but in this one it would suffice. However, now we're in a setting where we don't have eta equal to 0, and we are not willing to impose sub-exponential entries of the x's. The whole point of the talk here is to look at the case of heavy tails and potential contamination of the data. So one has to work a little bit harder. And in the paper, we construct an estimator, sigma n tilde of sigma, that does satisfy that you have this convergence here and probability here. So under the same assumptions as I imposed for the Gaussian approximation result, so there's no new assumptions, I have that this error here tends to 0. In particular, this variance covariance matrix estimator is built on using entry-wise a Winsorized mean estimator from a previous paper of ours, just for one-dimensional estimation. And then we use that. One can show that even in the presence of a little bit more than 2 moments only, these Winsorized means, they have sub-Gaussian obey sub-Gaussian concentration inequalities. Recall, even the sample averages in general don't have sub-Gaussian concentration unless you assume you're sampling from sub-Gaussian distributions. So that is quite nice about these Winsorized means, that they will have sub-Gaussian concentration inequalities in the presence of a little bit more than 2 moments only. This then allows us to do simply a union bound to estimate entry-wise these this sigma and tilde here. Okay. One could use other estimators as well, potentially. We haven't followed that route. That's what I write here in the last bullet point. For example, median of means type estimators or Catonius estimator. I hate my hyperlinks. Yeah, I was here, sorry. Good. So now denote by Z tilde the normal distribution, which has a covariance matrix of 0 and condition sorry, a mean of 0 and a covariance matrix of sigma and tilde. That is my estimator here, conditioning on the data here. And I denote now by rho and tilde the difference between my statistic of interest falling with the probability of my statistic of interest, the Winsorized means, falling within a hyperrectangle, and I compare that to the probability here of a normal distribution up here with this covariance matrix here falling within that same hyperrectangle. What I then can do is, of course, to subtract this probability here, then the probability of S and W falling within H compared to the probability of Z falling within H is exactly rho and W. I recall from here my definition of rho and W. Then I add back this probability of that falling within H. So I subtract and add this probability here. So that's why the second term here is just supremum of this probability here compared to this probability here. But now this guy here has a covariance matrix of sigma. This guy here has a covariance matrix of sigma n hat. But I've just argued that sigma n hat, sigma and tilde, sorry, is close to sigma. So I can apply this Gaussian to Gaussian comparison inequality to show that this guy here also converges to 0 in probability. And from that observation, this next theorem follows. Namely, under the same assumptions as always, it holds that now rho and W tilde converges to 0 in probability here. Okay, so this is fully feasible. I can sample from this distribution here. Now, in the paper, we also studied Gaussian and bootstrap approximations to studentized Winsorized means. That is, so far, I haven't divided through by an estimator of the variances of the uncontaminated data. But in practice, if I want to use things for testing, I may first put my data on the same scale. So that may be useful. One could also, instead of Winsorized means, study trimmed means. That is, instead of Winsorizing small and large observations, I could throw away the smallest and largest observations. What I want to do now, oh, sorry, I have one more thing I want to say. So concerning these Gaussian approximations, what we've shown is that uniform Gaussian approximation distribution of plane sums over hyperrectangles are possible only over class of distributions with light tails, if you want one's dimension to grow at an exponential rate. The keyword here is uniform. Of course, there exist distributions, well, not of course, but there do exist distributions such that this Sn, the distribution of Sn, can be approximated by that of a Gaussian, even though one has heavy tails, but not uniformly, because I construct explicitly distributions for you for which the approximation does break down. In particular, a phase transition occurs here, so one cannot hope for such uniform approximations to be valid beyond a polynomial growth rate of dimension d in the sample size n. However, for Winsorized means, one can have the dimension grow at an exponential growth rate in n. What I want to do now in the last 5-10 minutes of the talk is to give some consequences for hypothesis testing of these two results here. So imagine I want to test the global null hypothesis of a mean vector mu being 0 versus a mean vector being non-zero. An actual test for this hypothesis is to look at, I don't know why it changes slides like this now. An actual test is to reject if Sn tilde, the maximal entrance of Sn tilde falls above a certain critical value here, where Sn tilde here is my sum, which I've now standardized here, okay? So now, where Snj is just the usual variance estimators, okay? That is the sum of xi minus xi bar squared for each coordinate, okay? And CD alpha, here are the 1 minus alpha quantile of the maximum of a Gaussian here. So this is a natural sequence of tests to study. Okay, indeed, it is the case that if there's no contamination and dimension grows slower than this growth rate that I've been talking about many times, well, then such a test does have asymptotic size control uniformly over all distributions with a mean of 0, variance bounded away from 0 by some b1, and centered mth moment bounded from above by some b2. It is also possible to fully characterize the power function of such tests when dimension grows sufficiently slowly. Notice in the literature, even for looking at such sums as n, people have focused mainly on Gaussian approximations of Sn when they have a mean of 0. Of course, the second result here, to characterize the power fully, one must also think of Gaussian approximations under the alternative, so to speak. So there's some difference there to existing work. In any case, what I say here is the rejection frequencies, that is the probability of my statistic here falling above the sequence of critical values, can be approximated by a limiting Gaussian experiment, namely by the probability of the supremum of a Gaussian vector with the variance covariance matrix being the correlation matrix of the x's. Why the correlation matrix of the x's? Well, recall I've standardized my random variables here, so they all have a variance of 1. Hence, it's conceivable that what enters here is not the covariance matrix, but the correlation matrix. And then there's a mean shift here. Okay, now I also want to say that this sequence of critical values is the smallest possible data-independent critical values that one can use, ensuring that this sequence of tests here hold the size over this family of sets here. It is to say, one can construct distributions P within this class here, such that if I use smaller critical values, then I no longer hold the size here. At least the critical values are minimal up to terms of order 1 over square root log d, I believe I write here. Now, there do exist distributions within this family here for which the asymptotic size is less than alpha. In particular, if I have correlation matrix that consists of ones only, such that my maximum is essentially a maximum of one random variable only. So even though I have a d-dimensional vector, if all the entries are a copy of the same random variable, well then of course this maximum here is just one-dimensional in a sense. Then the rejection frequency would tend to 0 actually, because this CD alpha here, one can show that they grow at a rate of square root log d. So this is sequence tending to infinity, but this would be bounded in probability here. So for some distributions, these critical values may be too small, but uniformly, in a sense, the critical values are minimal. Okay, now I will not talk more about the proof here, I think. Let me just see. Instead, I will talk about test-based and Winsorized means. So, of course, instead of looking at the plain sums, I can look at my standardized Winsorized means here, where the sigma tilde nj is the diagonal elements of this variance-covariance matrix estimator that I spoke about 7-8 minutes ago. Then instead of taking a supremum of plane sums, I can take a supremum of winterized sums, but I take the same critical values here. Now the next theorem will show that this sequence of tests phi n w has the same asymptotic power function as phi n, but the characterization remains valid in much higher dimensions, okay? This is, of course, in some sense sensible because I've been saying multiple times now that Gaussian approximations to the distribution of plane sums break down beyond a certain polynomial threshold, while those for winterized means keep holding or maintain to be valid. So, under this growth condition that I've been talking about many times, that logarithm of dimension doesn't grow too fast, well then I have the same asymptotic size control of this sequence of tests here. And what is more, the Gaussian approximation for my rejection probabilities is the same as that for my plane sums. So notice here I have the probability of the supremum of winterized means falling above CD alpha. Here it was for the plane sums. But the approximating limiting Gaussian experiment is exactly the same. So that is to say, whenever there's no contamination, whenever dimension grows sufficiently slowly, then these two sequences of tests, those based on plane means and those based on winterized means, have both hold asymptotic size and have identical power functions. This is not clear from the outset because those winterized means I cut away the tails, so potentially maybe I could have lost some power by cutting away the tails. What is more is the following. Yeah, so not only do the tests have identical asymptotic size and power when the stronger assumptions of theorem 5, the theorem for plane sums, is valid, it is also the case that when d grows at an exponential rate in n, far exceeding the polynomial threshold that sums must obey, well then my test phi n w based on winterized means still holds the size and still has a Gaussian approximation to its power functions, So that's what I say in these two bullet points here. Oh, and of course, I also allow for a little bit of contamination. The last thing I quickly want to mention only is that it is possible to replace these sequences of critical values from a Gaussian by data-dependent critical values. So I can instead look at the 1 minus alpha quantiles of a normal distribution with variance-covariance matrix being my the square root of my estimator of the variance-covariance of the correlation matrix, and then consider this sequence of tests here. It is the same as the sequence of tests here based on winterized means, but instead of using a Gaussian approximation, that is the CD alphas from the limiting Gaussian, with an identity covariance matrix, I now sample from a limiting Gaussian whose correlation matrix is my estimator of the correlation matrix. For this sequence of tests, one can show that no matter which p in the null I consider, the rejection frequency will be close to alpha. So this result here is of course stronger than this result here, which only guarantees that for some distributions the rejection frequency will be alpha. But as I alluded to, there could also be distributions satisfying the null for which the limit superior is much less than alpha. And this sequence of tests here, one can show that it never has lower power than the sequence of tests phi n w I want to write here. Namely my sequence of tests based on the winterized means. In fact, it's also true for the sequence of tests based on plane means, because the sequence of tests based on winterized means and plane means has the same asymptotic power function. So I never lose anything. But one can also show that for many distributions, it doesn't help to use these data-dependent critical values. In fact, the asymptotic power functions are the same. But for some distributions, it can help a lot, because there exist distributions for which it is the case that phi n b, phi n w b are meant to write down here. That is my sequence of tests based on winterized means, but data-dependent critical values. can be consistent, but if I instead use phi n, the one where I don't use data-dependent critical values, I have asymptotic power 0. So a asymptotic power gain of 1, the most one can hope for. I think I will leave it at this because I said I would speak for 50 minutes only.
Wonderful. Thank you so much, Anders. That's a brilliant presentation. Wonderful paper by you and David, as usual. So thank you very much indeed. I will stop the recording now and we'll move to the question and answer session.